Welcome back. Today we have one of the most expensive, most overrated 1080 Ti's from ASUS that's actually a piece of junk compared to 1080 Ti from EVGA. And soon you'll see why that is. So the card came with no image. Let's take it apart and see what's wrong. We will get back to the cooling issues, but first, let's take some measurements so you can reference them if you need to. 12 volt kilo ohms, 3.3 kilo ohms, 1.8 700 ohms, 60 ohms on PEX, kilo ohms on this 12 volt line. These two are also 12 volt coming from the external power cable, and 5 volt is 700 ohms. Memory was 60 ohms. I forgot to record that step. My apologies. Now let's see if the first data pairs are in good shape on both sides. Measuring in diode mode, we placed a negative on the ground and a positive on one of the data line pins. Reading should be the same, more or less. On the back side, I'll check the PEX reset. Then the reference clock plus and minus. Then I'll check the first data line as well, except this time I'm touching the probe after the capacitor. Same reading, suggesting that this is all is well. Without any red flags, let's power the card and see how many amps it likes to draw. And it looks like it's drawing about 1.5 amp. That's a reasonable number for 1080 Ti. Now I'll power the card through the PCI riser so we can look if it generates required voltages. 1.8 present, 1 volt on PEX, 138 and 5 volts are present, and obviously the 12 volt is here and all good. Alright, let's plug this card in and see if it works. And I'll run a memory test along with the first launch so that I won't have to boot twice. And it looks like we have a picture, which is a good sign, and even the memory test passed. So why did the seller say it was broken? I don't know. Maybe there's an issue with the data lines? It all looks good to me. Okay. What if this card has a bad memory signal like one of the Gigabyte in my previous videos? So let's test that. Nope. That signal looks good. Okay, whatever. Let's plug it in and see. Maybe we don't even need to fix anything. Wouldn't that be a good day? Paying $250 for a broken card that actually works. You heard me. These things aren't cheap. That's why I need your support with the comment, likes, and maybe if you can go as far as subscribe to my channel. It'll really help me out. Thanks. Anyway, as you can already see, the card seems to work, but the foremark is frozen. And the second time I ran it, it was working seemingly fine, as if nothing was wrong. I tried it over and over and I could not reproduce this, as if it fixed itself somehow. Don't you guys love when you get a card like this? And then I run an actual gaming engine, and that's where a problem became consistent. As soon as the gaming engine loads, it freezes either right away or shortly after. What's interesting about this is if I blow compressed air on the memory face trying to cool it down, things get better. We've had similar problem with Gigabyte cards, and the reason for this problem is the same, believe it or not. Looking at the assembled card PCB, The area of the memory phase looks like dark chocolate. If you watch my previous video where Gigabyte forgot to put thermal pads, it was one-time incident, at least for me it was. But for ASUS, this is normal. A high-end, most rated, most expensive card comes with no memory phase cooling. And that, ladies and gentlemen, is the reason why I don't like ASUS cards. Too much money for an intended future malfunction. Okay, with that we can suspect that there is a memory problem, but we can't seem to identify it because we can't run a game and a memory test at the same time. So I ended up running a series of different memory tests with higher frequencies to see if anything would show up, and it did. Here are the two test results. First test shows a bad memory chip, and the second test shows two completely different bad memory chips, which means the problem is not the memory chip, but the circuit. So let's take it apart and see if we can identify what contributes to this behavior, and I'll show you how to fix this in the end of the video. Stick around. Let's take a closer look at this marvel of ASUS engineering. This high-tech aluminum frame makes absolutely no contact with the heatsink, so whatever heat it will accumulate coming from the memory chips will not be dissipated. The aluminum shield in the back is also practically useless. No thermal pads there to soak up any heat anywhere. And here is the greatest design choice ASUS came up with that led this card to my desk. There's absolutely no cooling for the memory phase. Coils and the MOSFETs are completely exposed and nothing is making contact with the heatsink, as if they purposely cut away this section to make it run hot. The only place where this weird aluminum frame makes contact with the heatsink is this pad here. But it's also useless because the contact surface area is very small. It rests on the edges of the heatsink ridges. If the area of contact was flat, like they are here, it would provide better surface contact. But even with that, it's still bad. Okay, I guess all I can do at this point is to guess which component can no longer be stable under load. And as before, the main suspects are phase controller, MOSFETs, and as we've learned from our previous video, these capacitors here, so let's start. I'll assemble everything back together and see if we have any changes. And if you look here, we're still having a lag, but at the very least it's not freezing anymore, so we're moving in the right direction. Also, I increased the fan speed to bring the operating temperatures down, and it looks like it's getting better and better, which means we're definitely moving in the right direction. This capacitor here was also exposed to a lot of heat coming from the memory phase, and it looks yellowish. This cap is a suspect and is cheap to replace, so why not? And I don't have this exact capacitor with flat legs, but I do have this one cap that has the same rating and the same dimension. So I'll put it in there like that, and as I later found out, this capacitor change had no effect whatsoever, which means that you and I had learned something today. Next on the list is this guy, PMU11 on the board view, and UP1666Q on the schematics. I just happen to have like 20 of these, so let's replace that as well. That looks beautiful. Let's see if it makes any difference. And it does. As you can see, lag now is hardly noticeable. I think we're almost there. There's a second line of capacitors on the back. I will replace those as well, just in case. Okay, that looks really good. Before I go back testing the card, let's address the cooling problem with the memory phase. First, I want to find out how thick the thermal pad I need. For that, I'll place a ball of Play-Doh and squeeze the card as if it was assembled. I'll remove the dough and measure its thickness. And it looks like we have just under 6 millimeters. The thermal pad I have is not made of silicon. It will act as a Play-Doh instead, so I can make it pretty much any thickness I want. And for this situation, it works really well. Also, you can see here that I purposely flatten the ridges of the heatsink in the area of contact. So that way the thermal pad will have a better surface contact, better heat transfer as a result. Now let's see if that has any positive effect by running yet another test. And we have a smooth takeoff, smooth flyby, and I think this is it for this card. And as for you, if you guys find this video helpful and interesting, please put a comment below. Like this video and subscribe for more, and I'll see you later. Bye bye.